We all have a feel for what temperature is. After all, one of our basic senses is dedicated to it. But it is much harder to get a grip on what it actually is physically. It's not like distance, where we can just take some stick as our basic unit and then measure and compare all distances in a straightforward way. The historical development reflects this. For centuries people debated whether heat, the underlying quantity to temperature, was a substance enveloping and suffusing ordinary matter, or whether it was the cumulative effect of microscopic motions of the underlying particles. And in the latter case, were the particles flying freely through space, or were they vibrating around fixed positions? Was there a lower limit to temperature, where all motion ceases, or where the heat substance is completely absent? Could heat be created or transformed into something else? The first progress made on temperature was an advance in measurement. More and more accurate thermometers were built. That was certainly useful, but there was still no sound underlying theory, since it wasn't even clear what was being measured exactly. The measurements were based on the observation that matter, in particular liquids and most of all gases, expanded when their temperature increased. And so you could measure temperature by measuring the degree of expansion of a test substance. This assumes, of course, that there is a linearity in the expansion with temperature, and there was good reason to believe that, at least in a limited temperature range. You could check, for example, that a 50-50 mixture of boiling water and water that was very close to freezing would land right in the middle between the boiling and the freezing temperatures on your thermometer. Still, what was actually being measured on a microscopic level was far from clear. But then, in the second half of the 19th century, came statistical mechanics. It was recognized that there was no heat substance. Heat really was the chaotic motion of atoms and molecules, which, in very large numbers, give rise to predictable microscopic phenomena, which can be analyzed using probability theory and statistics. In addition, based on theoretical considerations on the efficiency of engines, Lord Kelvin found that there was in fact a temperature of absolute zero, and constructed the temperature scale named after him from the two requirements that it start at that absolute zero, and that the interval between the freezing and the boiling temperature of water be split into 100 units. So basically it is the Celsius scale shifted down to absolute zero. Around the same time, the modern concept of energy was formulated as an abstract quantity that could manifest in all sorts of ways, like the motion of a planet or the tension in a spring. In particular, heat, being nothing but microscopic motion, was one of its building blocks. Macroscopic motion could in fact be converted into heat. And to some extent vice versa, as in steam engines. The concept of inner energy, denoted U, plays a crucial role here. The inner energy of an object is that energy which it has not in relation to something external, like the height of a boulder in the gravitational field of Earth, but only due to its internal composition. For a gas, that would be the energy in the motion of its constituent particles, their free movement through space, their rotation and their vibration. With statistical mechanics came a new quantity and powerful tool, the infamous entropy. The basic idea of entropy is that the random motions of atoms and molecules tend to produce those states that are very unspecific in terms of the microscopic arrangement, just because there are many more ways to arrange the particles that way. When you have a large number of atoms at random positions in a box, chances are about half will be in the left side and half in the right side. It is very unlikely that all of them will be on the left side, just because there are many more ways to arrange the atoms for the 50-50 mixture. You might think that gases are very well distributed because the molecules push each other away, but that is not the case. After all, in a gas usually most space is completely empty, and long-range interactions between the molecules are very weak. It is all about probabilities, hence the field's name of statistical mechanics. So the atoms in your room could, in principle, spontaneously all find themselves in the left half. But with the large numbers involved, that is just overwhelmingly unlikely. For 100 particles, there's a decent chance of finding, say, a 60-40 mixture. All in the left half, though, is already very unlikely. But if we increase the particle number, even the tiniest of deviations is incredibly unlikely. And even for just 10 billion particles, which as a gas is not even enough to fill the volume of a typical biological cell, the spread in the distribution becomes essentially nil. For a macroscopic volume of gas, made up by n particles, where n is Avogadro's constant, this will fill about 22 liters of volume at standard temperature and pressure. We can calculate the number of times k we have to observe the gas in a random configuration until the chance of finding all particles in the left half at least once is 50%. We get a number that is approximately 2 to the power of 10 to the 23rd. It's hard to overstate how humongous this number really is. The power itself is already huge compared even to astronomical numbers. It's about 1,000,000 times the age of the universe in seconds. And of course 2 to that power is much larger still. And it's not just that these extreme deviations are incomprehensibly unlikely. Even deviations that are completely insignificant to us essentially never occur. And that is why the density of the air around you is very nearly constant. We don't live in a free-floating box and so there are some deviations, particularly due to gravity, which pulls the particles downward, so that the density decreases with height. Enough so that at the lower end of a helium balloon, so many more air particles are bouncing against it than at the upper end, that the net force imparted to it that way is stronger than the gravitational force pulling it down. We call a macroscopic distribution, like the 50-50 mixture, or the one where all the atoms are in the left half of the box, a macro state. A micro state is a specific configuration of the system, where you assign each atom individually either to the left or to the right. Assuming that each microscopic arrangement will be found with equal probability, we will tend to see those macro states that can be realized in many different micro states. And so the macro state where all particles are in the left half is very unlikely, because there's only one corresponding micro state. Each atom must be in the left half. For the 50-50 state, on the other hand, there are many different microstates. We can, for example, switch any atom from the left half with any atom from the right half. The result will be a different microstate, but still a 50-50 mixture. And so if we define entropy as some kind of measure of how many microscopic configurations there are for such a macroscopic state, so that the entropy in our example is highest for the 50-50 mixture and much lower for the state where all atoms are on the left, we can restate the idea as the entropy always tends to increase. In the actual calculation of the number of microstates of a gas in a box, of course you have to take into account all the possible positions. After all, it matters not only in which half of the box the particle is, but that calculation is pretty complicated and relies on quantum mechanics. The essential point though remains, with really large numbers, particles are very uniformly distributed. Now the thing is, most physical systems, like plain ordinary matter, have more ways of arranging themselves microscopically for a given inner energy when that energy is higher. Just like a greater volume gives the atoms more ways of arranging themselves in space, a greater energy gives the atoms more distinct ways of distributing the energy among themselves. Let's see how that works in the case of a gas with just one single atom particle in 2 dimensions, for clarity's sake. The particle has some kinetic energy in the form of its momentum, which has 2 components along the 2 dimensions of the plane. These components are independent of one another. Any combination is possible in principle, but only when the energy of the particle can vary. When the total energy is fixed, while the momentum can still point in any direction, its magnitude is also fixed. The kinetic energy of a particle is its total momentum squared, divided by 2 times the particle mass, and that must now be equal to the internal energy U, since there are no other ways this one atom gas stores energy, except in the mass of the particle itself, but that is just a constant here, so we needn't worry about that. We can put the momentum into a 2-component vector, and then the equation reads square root of 2mu equal to the length of the momentum vector. Which means the vector lies on the circle of radius square root of 2mu in 2-dimensional space. Now the vector is one specific momentum microstate available at the macrostate defined by the inner energy U. So the set of all available microstates is the set of vectors which lie on that circle. the length or circumference of a circle grows when its radius grows, and so when u is larger, we have more momentum microstates available. Just like individual components of one particle are independent except for the total momentum being a constant, the momenta of different particles are also independent in the same way. And so if we take two particles moving in 2D, we have a total of 4 components, and our momentum space is the surface of the hypersphere, which is the sphere embedded in 4-dimensional space, again with radius square root of 2mu, and that area or volume is 2 pi squared times the radius cubed, which again grows with u. And of course we can generalize this and take 10 to the 23rd particles moving in 3-dimensional space, which gets us 3 times 10 to the 23rd momentum components, 3 for each of the particles. And so now our total momentum vector lies on the sphere of radius square root of 2mu in a space of 3 times 10 to the 23rd dimensions, the size of which again grows with u, and much faster at that, meaning that for higher energies, many more momentum states are available, and the entropy increases. Because of that, such systems have a tendency to take on energy from their surroundings, in the form of heat flow, in order to increase their entropy. But of course, the surroundings also want to keep their energy because it gives them a higher entropy of their own. And so in the statistical tug of war for energy, an equilibrium will be reached when the system's desire and the surroundings' desire for energy are in balance. Then heat will stop flowing and the temperature will stabilize. In that case, the total entropy S will be stationary, meaning that a small exchange of energy du between the internal energy u1 of object 1 and u2 of object 2 doesn't alter the total entropy, which is the sum of the individual entropies, since the gain in entropy S1 of one system is exactly offset by the loss in entropy S2 of the other system. Otherwise, there would still be heat exchange in the direction of increasing entropy. Note that here the derivative of S2 by U1 is equal to minus the derivative by U2, since an increase in U1 corresponds to a decrease in U2, and vice versa, when we keep the total energy U fixed. Usually that stationary point of the entropy will be a maximum, and the equilibrium will be stable, since a small disturbance lowers the total entropy and the system spontaneously reverts back to the original state. But it can also be something like a saddle point, where a small disturbance brings the system out of equilibrium again and heat starts flowing. Naively, we might expect the total entropy being stationary to mean that for a small transfer in heat energy from System 1 to System 2, System 1 loses as many microstates as System 2 gains, and vice versa, so that there is no reason to exchange energy because the sum of the microstates of both systems doesn't grow, but that is generally not the case. The issue is that the thing that is maximized, the total microstates, is not the sum but the product of the microstates of object 1 and 2. For every microstate in object 1 we can choose any microstate in System 2, and so the set of all composite microstates is the set of pairs of any microstate in System 1 and any microstate of System 2, and their total number is the product of the number of microstates of object 1 and of object 2. For example, if object 1 has microstates A, B, and object 2 has microstates 1, 2, 3, we can form a total of 6 microstates for the combined system. So entropy cannot just be the number of microstates, since the equilibrium condition cannot be that the two objects want more microstates equally strongly. It must be that not the sum but the product of the microstate numbers is stationary with respect to energy exchange, because then the total number of microstates doesn't grow when heat flows in either direction. So the derivative of this product by the energy of either of the systems must be 0. If it wasn't, we could shift some energy between the objects, for example lowering U1 and increasing U2, and that way increase the total entropy. We can simplify that criterion using the product rule and replace minus U1 by U2 to arrive at the real equilibrium condition. We must first scale the partial derivatives by the number of microstates of the other object, and then they have to be equal. The basic reason is that when we add some microstates to System 1, the contribution of that to the total number of microstates is scaled by the number of microstates of System 2, because we don't add but multiply the separate microstate numbers. Now the cool thing is that we can isolate the object 1 and object 2 parts to get an intrinsic quantity for each object that does not rely on the properties of the other object. The partial derivative of the microstates by the energy divided by the microstates. That can also be expressed as only the derivative by energy of a single quantity, namely the logarithm of the microstates. And so that must be the entropy, since that is exactly how we defined it, as the thing that two objects in equilibrium with each other want equally strongly. Plus, as you can check for yourself, the entropy, in contrast to the microstates, is additive. This is no happy coincidence, we constructed it specifically that way. Maybe you can spot where we did so. Now, based on this equilibrium condition, maybe it's starting to dawn on you that there might be a connection between that desire for heat energy, i.e. the derivative of S by U, and temperature. After all, temperature plays a similar role. Two objects in contact exchange energy in the form of heat until they are at the same temperature. Now the idea is that it's actually not just a similarity, those two are one and the same thing. There's one problem though. For temperature, it is lower values that give an object a stronger tendency to absorb energy. A colder object warms up by taking up heat energy from its warmer surroundings. In contrast, for the tendency to absorb energy on statistical grounds, it is a higher value of the derivative that gives a stronger tendency to absorb energy. So instead of being equal, they must in fact be inverses of one another. And so we define 1 over temperature as the partial derivative of the entropy by the inner energy. Now it makes sense. Lower temperature means higher inverse temperature, corresponding to a higher tendency to absorb energy. One ambiguity remains. Entropy can be defined as any arbitrary constant times the logarithm of the microstates omega without any change to the physics, since the constant just cancels out when we compare two entropies. But now we are not just relating one entropy to another, we are relating entropy to an independently measured quantity. Our temperature scale was not constructed with the number of microstates in mind, but with the freezing and boiling point of water. So now it is important that we do use the correct constant, if we want to stick to the Kelvin scale. We could of course also adjust the Kelvin scale and drop the entropy constant, but since historically the Kelvin scale was already established when entropy came around, it is the entropy that needs to budge. So entropy is that constant times the logarithm of the number of microstates that makes the thermodynamic definition of temperature correct in units of Kelvin. How do we figure out that constant? Well, we can look at a specific system in some configuration where we know a formula for the temperature as a function of the known properties of the material, like particle number n, volume v, and inner energy U. We construct the entropy of that system, also as a function of these properties, in particular the inner energy, by explicitly counting the number of microstates. Then we put the expression for the temperature and for the entropy, which includes the constant factor we need to calculate, into our definition of temperature and solve for the constant. This way we can simultaneously check that the behavior of temperature defined this way is in line with what we want temperature to be traditionally in that situation we are analyzing. If we find, for example, that our constant is not actually a constant, but depends, for example, on the volume of the substance, then we know that our definition of temperature cannot be right. For the simple standard example of an ideal non-interacting monatomic ideal gas, the entropy can be explicitly constructed. It's a relatively complicated calculation, so we won't do it here. The result is called the Sackur-Tetrode equation, and if you are interested in the derivation, you won't have any trouble finding one online or in a thermodynamics textbook. Now we can take the inverse of the derivative of that entropy by the inner energy U. We obtain 2/3 times the inner energy per particle. Now at temperatures that are not too low, we can use the equipartition theorem for our next step. It states that at not too low temperatures T, every degree of freedom has energy 1/2 times K times the temperature, where K is the Boltzmann constant, which can be determined experimentally. What's a degree of freedom? It is one way in which a system can store energy. For example, one of the molecules in a gas might be vibrating or rotating. In our case, where we have a monatomic ideal gas, there's only one type. Translation: atoms moving through space in straight lines. There are 3 independent degrees of freedom per atom. How it moves along the x-axis is independent of how it moves along the y or the z-axis. And so for a monatomic ideal gas with n atoms and 3 degrees of freedom for each of them, the equipartition theorem tells us that the internal energy is U equal 3n times 1/2 times k times the temperature. We insert that into a formula for the temperature and find that A is just the Boltzmann constant K. So we finally have our complete definition of entropy, and with that of temperature. Now let's have a look at a specific example, the paramagnet. The calculations are pretty simple here, much more straightforward than for the ideal gas, but the results are pretty counterintuitive, and so we see how this new definition of temperature is a much more general tool than the naive measurement-based version was. A paramagnet is a collection of little magnetic dipoles. You can think of them as little bar magnets, but actually they are subatomic particles like electrons, with a property called spin half. The details are not very important for our purposes here though. The fields that bar magnets and electrons produce are basically the same, but there's one important difference in how they behave. When we apply a constant magnetic field throughout the collection of dipoles, a macroscopic bar magnet can of course take any orientation relative to the direction of the field, while an electron will have one of two orientations relative to the field, either against or along it. We can represent them as little arrows pointing either up or down. Now, a homogeneous magnetic field doesn't push a dipole in any direction, but it does exert a torque on it, trying to turn it until the dipole field is in line with the applied external field. So a dipole oriented against the external field will have potential energy, since it can be accelerated in a rotation through the field. And when it is oriented along the field, it has less energy, since we need to spend some energy to turn it against the torque of the external magnetic field. Since the dipoles have one of these two positions, they will either have some definite high energy E0 or low energy minus E0. E0 will depend on the type of dipole and on the strength of the magnetic field, but for simplicity we can just set it equal to 1. If we have n such dipoles, at any moment there will be n up high energy dipoles and n down low energy dipoles. The internal energy of the system will then be the sum over the individual energies of all the dipoles, U equal n up minus n down. To find the temperature of the system we need to calculate its entropy, and for that we need to figure out the number of microstates to any given macrostate. A macrostate is defined through the total energy U of the system, given by the numbers n up and n down. N up tells us how many dipoles will be in the high energy state. It doesn't tell us which those are. That is why we call it a macrostate. It only tells us about the overall properties of the system. A microstate is given by assigning each dipole one of the two energy states it can occupy. So how many different such configurations are there for n up equals 3, n equal 5? Well, we can just explicitly construct them and find that there are 10. But now let's go through that more systematically. Essentially what we need to know is how many distinct ways there are of grouping the 5 dipoles such that 3 land in the up category and 2 in the down category. Let's label the dipoles by 1 through 5 so we can keep track of them. Then let's say we get a new grouping by swapping out 1 and 5. This is the same macrostate since we still have 3 up and 2 down. But it's a different microstate since 1 and 2 each flip their orientations. So the number of microstates for a given macrostate is the number of ways to group the dipoles, disregarding changes that only occur within the two groups, rather than between them. That number is the total number of permutations of the dipoles, n factorial, divided by the number of permutations of both the up dipoles and the down dipoles. Now to calculate the temperature, we need to find the derivative of the entropy by the inner energy. So let's begin by calculating the number of microstates, not as a function of n up and down, but of the inner energy. We use the fact that n down is equal to n minus n up, and substitute that into the formula for U. Then we can solve for n up in terms of U and substitute that into our formula for the microstates. When we plot the microstates against the inner energy, we find a curve that is symmetric around the inner energy 0, with a maximum at that point. When we increase the number of dipoles, the relative spread of the distribution gets narrower, similar to the probabilities for the particles being in the left box. The most interesting thing about paramagnets though is that the number of microstates doesn't continually grow with increasing energy. Once half the dipoles are in the high energy configuration, the number of microstates stalls and then actually starts to drop for increasing energy. So the same will be true of entropy. Now let's look at the temperature. We calculate it based on the definition we have constructed, using the Stirling approximation for the logarithms of the factorials, which is very accurate so long as the numbers are not too small. Plotting it, we see that the inverse temperature is negative for positive energy values, corresponding to the entropy sloping downwards with increasing energy. So in contrast to everything we are used to, this is a system that in some states actively wants to lose energy. Even in contact with the hottest object, heat will flow from the paramagnet to the hot object. If we also plot the temperature itself, we get in trouble. Its inverse is 0 in the center, and so the temperature diverges there. Worse, it diverges in different directions, depending on where you approach the center from. But this makes sense. The fundamental quantity here is the inverse of the temperature. It is defined as a well-behaved function of fundamental quantities, and there's no reason to expect the same to be true for the temperature itself. So in a sense, the inverse temperature is the more fundamental and elegant quantity.